All right, so what we want to find is the area between these two curves. And the way I like to think of it, because it's really helping me set up what we're going to do in section 6.2, I like to think of it as, let's see, there we go, as starting out by finding the area of one slice. So I always like taking slices through my regions. It gives me a nice geometric interpretation of what I'm doing. And so I want to find the area of that one slice. Now the area is going to be the width times the height. We'll see if we can't figure out what the width and the height would be. So area of one rectangle. Well, the area of one rectangle is going to be the width times the height. And the height is kind of nice because it's just going to be our dx term. But it's important to have that dx term there because that tells us what you're integrating with respect to. So I've got a dx here, and now the height is going to be the top function minus the bottom function. So what's the top function in this, Larnell?
I believe the top would be, I think that's cosine.
So it would be our 8 cosine of x minus secant squared of x. And the reason I'm so picky about this dx term is because it tells you what you're integrating with respect to. Now, sometimes you have to take slices horizontally, and a horizontal slice would be a dy slice. But that's not going to work very well for us in this particular case. All right, now that's the area of one slice. And, you know, if we were doing this as an approximation, then we'd add the area of another slice, and then the area of another slice. And we keep on adding these areas until we get an approximation of the whole area. Well, you know, we can do better than just approximating. And the limit of a sum of all those areas, so the limit as the sum of these areas, or as these delta x terms, dx terms get really, really small, limit of sum, should be delta x, is going to become our integral, our definite integral. And you know, I'm doing a quick job of skirting past this, but it's really the basis for what we're doing, and the fundamental theorem helps us out here as well. So to add all these up and let our rectangles get really, really small is equivalent to integrating. So I'm going to integrate 8 cosine of x minus secant squared of x dx. Well, where do you think I should integrate it from? From where to where? Well, yeah, so that's going to be these right here. That's going to tell you, all right, we're going to start our integration here and end it here. So from negative pi over 3 to pi over 3. This is a great one to start out with because there's another little trick or something that I can show you here. One of the things that catches my eye is that I've got a symmetric interval. So that is, I'm going from pi over 3 to negative pi over 3. So I'm like, oh, well, that's cool. And then you start to look at the function and you realize, well, cosine's an even function and secant's an even function. In fact, you can see that here because both of these are symmetric with respect to the y-axis, right? So if I folded this graph over on the y-axis, the left-hand side would match the right-hand side. It'd be perfect. So instead of finding the area from negative pi over 3 to pi over 3, how about we do this? Let's take and double the integral from 0 to pi over 3. Does that work? Do you see why we can do that?
I don't really get that.
Well, you see the area where I have everything shaded with the rectangles, the purple one, the blue one, the green one?
Yeah.
To the right of the y-axis.
Yeah.
That area to the right of the y-axis is a mirror image of the area to the left of the y-axis, right?
Yeah.
So rather than calculate the whole area from left to right, I'm just going to calculate the area on the right and double it. So
Okay.
this area here, and now I'm shading it all in yellow, that's half of my area. So if I calculate that area and double it, well, then I'll get the same result.
So you can do this with basically anything that is kind of like, you know, when it's like basically look like the same thing on both sides.
Yeah, it has to be, you know, has to be symmetric with respect to the y-axis. And the more technical term for it mathematically is that it's an even function. So minus secant squared of x dx. Okay. So let's continue then. I'm gonna just move this to another page. So let me see if I can't do it this way. So I'll copy that. Does that work? Can I copy that? Copy. Yeah, there we go. And let's put that in a new page now. So paste. Wow. You have to pardon me that I impressed myself. I didn't know I could pull that off. Okay, so I need some antiderivatives here. So what are those going to be? Well, it's going to be twice 8, 0 to pi over 3. What's the antiderivative of cosine?
That's negative sine.
I think it's just sine. Because derivative of sine would be cosine. I mean, personally, I always have to check myself. I'm like, okay, is it sine or negative sine? The derivative of sine would be cosine, so I think we're okay there. How about the antiderivative? What do I differentiate to get a secant squared?
Tangent.
Tangent, yeah, thank you. So minus a tangent of x, which is going to be 2 times, let's see, 8 times sine of pi over 3 minus tangent of pi over 3 minus this at 0. But if I put in 0 for sine and 0 into tangent, both of those are going to be 0. So I'm just going to make kind of quick work of that. So let's see what we're going to be left with. It's going to be 8 times pi over 3, or sine of pi over 3. Sine of pi over 3 is root 3 over 2. Tangent of pi over 3, I think, is going to be the square root of 3. So let's keep going. The 8 and the 2 cancel. That'll give me 4 square roots of 3 minus square root of 3. How does the middle simplify? Anyone?
3 to radical 3.
3 roots 3, thank you. So overall, 6 square roots of 3 should be your final answer. Now, just kind of a heads up, I think I've tried to mention this a few times in the email. I do want to see a little bit more work this time on your exam. I saw people on the last exam going from something like this to the correct answer over here in one step. And even for your instructor, that's a little bit of a stretch. So I'm a little anxious when I see such big leaps of faith. I want to see a little bit more work there. But hopefully that answers your question there, Nell.
Yeah.
We're good on that one?
Yeah.
All right, excellent, excellent. All right, appreciate the question on that. What else we got today? Who else has got one? I see a lot of people here. Asim, Sobher. All right.
I don't know what you guys, because I just came in, I just came late. I don't know which problems you guys did. I'm assuming they're from section 6.1.
Yeah, that was section 6.1. So,
because I had some questions on 6.1 also, but they're from WebAssign, from the WebAssign homework.
Well, this was from WebAssign. So you can see the problem here, and you can review it in the notes, or excuse me, the recorded session afterwards.
Okay, so, because I had a problem with number 8 and 9, so I don't know if that was one of them or not.
Okay. Well, what's problem?
That was number 9.
Oh, that was number 9. Okay.
Okay.
So why don't we take a look at problem number 8 together? If you can just read me what that is, that'd be great. So here's our two curves, 14 minus x squared, that's the parabola that faces down, and x squared minus 4, that's the parabola that faces up. We want to find the area between these two curves, so that's this area in here. And we're going to do that by starting out with a little slice in this region. And I want to find the volume of this one slice. Now I'm drawing a rectangle here, at least as best as I can. And let's see. I want to find the area of this rectangle. So the area of a rectangle is a pretty easy figure to work with. Area is going to be the height times the width. Now the width of this is just going to be the direction in which this slice was taken. That's a dx slice. The height is always going to be the topmost function minus the bottom. So top minus bottom. Let me see about that, top minus bottom. Let's see if I can't move that down here. There we go. Top minus bottom. So let's figure out expressions for each of these. The top function is going to be your 14 minus x squared. It's going to be 14 minus x squared. And the bottom function is going to be x squared minus 4. So all of that is going to get multiplied by the width, and the width is dx. Now the nice thing here is that these things match. It is the fact that I've got a dx here and that this expression is also an x match. They have to match. And I point this out as a double check for your work. We can simplify that expression. So that's just going to be 18 minus 2x squared dx. Now that's the area of one of these. To add up the area of all such possible rectangles, even if they get arbitrarily thin, we're going to need to integrate. And the big question for integrating is, well, where am I going to integrate to? My region extends from here to here. Now you can reasonably guess that that goes from, say, 3 to -3. But if you didn't have a good graph and you didn't have such easy functions, what would you do? Well, you'd have to solve a little system of equations to figure it out. So what you could do would be set these two things equal to each other. So 14 minus x squared equals x squared minus 4. I'll add 4 to both sides, and I'll add x squared to both sides, and I end up with 18 equals 2x squared. Divide both sides by 2. 9 equals x squared. So that tells me that x equals plus or minus 3. And that's what we're seeing down here. We're seeing that we have two solutions at 3 and -3 where these two lines cross each other. That gives me my limits of integration. -3 to 3 of 18 minus 2x squared dx. Okay, so how are we looking there? Are we okay with the setup? You're unmuted.
Yes.
Looks good.
Okay, thank you. Now, I'm not sure how much of the last problem you caught, but some of you guys should be able to tell me something interesting about this. Because like the last problem, what I'm seeing is I've got a symmetric interval again. I'm going from -3 to 3. That's a symmetric interval. And this is just a nice thing to do to be helpful for yourself. So how does that information help me? Anyone?
You can use it as twice the integral of 0 to 3.
Perfect. That sounded like Don. Well done. So the left half and the right half of this region are symmetric. So instead of computing it for the whole thing, I'll just double the integral from 0 to 3. And it may not seem like a lot, but boy, it's just nice and handy not to have to plug in a negative number. It really is. So that's going to be twice the function from 0 to 3 of 18x minus, what, 2/3 x cubed? And it's just easier to plug in a lower limit of 0, right? So it's going to be 2 times 18 times 3 minus 2/3 times 3 cubed minus, and this is the nice thing, the lower limit is just 0. So rather than having to plug in a -3, I think we're in much better shape. So let's evaluate this. That's going to be twice 54 minus 18. So that, I think that's 72. But you guys can check me because I was never really good at math.
Yes, it is.
All right. Awesome. Awesome. Okay. How are we doing on that one? That one good?
Okay, that was pretty good. I found out what my mistake was.
Okay, good, good.
Thank
So we're going to take this figure and rotate it around the x-axis. And kind of like what we were doing in section 6.1, I like to look at a little slice of this region. So that's going to be right here. That's going to be my slice. And I like to figure out what happens to that slice as we rotate it around the x-axis. So let's see if we can't set that up. Now, when we rotate it around the x-axis, can you tell me what shape that's going to be? What's just the slice? You don't have to envision the whole region. Just vision the slice.
That's going to
What's
be
going to happen when we rotate it around the x-axis?
That's going to be a
hockey puck. Perfect. Yeah. So the volume. Oops. Volume of one puck. Now let's put hockey in there. So I don't know if there's any hockey fans out there, but I saw a cool meme. It said, day 11 without hockey. Went out in the forest to watch the Bruins destroy the Leafs. And of course, the Bruin is a type of bear. They showed some bears eating some Leafs. It was pretty cute. All right, so that's actually a reasonable hockey puck given my constraints of drawing with this pen. Now I want to find the volume of that one puck. And the way I like to think of the volume is I again want to break it down. It's going to be the height times the area. So area times the height. And let's take a look at our slice over here. That slice, when we rotate it around, gives us this hockey puck, which also, in thinking about it, looks kind of like a roll of toilet paper. Maybe that's indicative of the times we're in, I don't know. But what's the width of that slice?
That's our dx.
That's a dx. Excellent. So that's a dx slice. And that's going to be the thickness here, or what I'm calling the height. Now, the top of this figure has the shape of a circle. And we know the shape of a circle, that's just pi, or the area of a circle, that's just pi r squared times dx. So we're getting closer to an expression for the volume. The last thing that we need is to figure out what the radius is. And the radius is going to be the distance from this point here on our slice to the x-axis. So let me do that here. That's going to be r. So what's an expression for r going to be for us? Well, r is going to be the top minus bottom, right? Top minus bottom. And I need to have that in the variable of x. So the top function was x plus 1. The bottom function, well, it's not really a bottom function unless you want to count it as 0. So top minus bottom, x plus 1 minus 0. That gives me x plus 1 squared dx. So that's my expression for the volume of one puck. And that's the hard part here. So let me pause for a second. Maybe I was going a little too fast someplace and you need a little help, but that's what we're going to work with. So are we comfortable right here?
Yes.
Okay, thank you. Now, to find the volume of the entire region, and when we rotate it around the x-axis like this, you're going to get, you're going to get something kind of filled in here. I don't think that this shape is the right one for what you're going to have. But our graph, when we rotate it around the x-axis, is going to give us kind of a cone shape that I'm trying to shade in yellow here. So that's roughly what it'd be like. This other stuff doesn't apply to this particular graph. So to finish this up, we're going to have to integrate. And we'll integrate from, well, let's see. Let's put the pi out here. I've got x plus 1 squared dx. And let me ask you, Alonzia, where
Yes.
should I integrate from? And to decide that, think about where you could take this slice in the region and still be in the region. So how far to the left can I move it? How far to the right can I move it? Where are the extremes that are going to be my limits of integration? How far over to the left can I move this and still be in the region? Can I move it over to x equal 1? Can I move it to x equal to -1? -2? Where's the 0? Good. 0 on one end, and what's on the other end?
4.
4. Nice. Nice. Does that help out?
Yes.
Now, personally, what I kind of suggest is that you can double check yourself by numerical integration. And you can do that on your calculator with fn int from 0 to 4 of x plus 1 squared. Squared. I'm just doing that on my calculator here real quick. You know what? I can do it here. Let's do it here. Now, this is a pretty quick polynomial. If you're doing this for yourself, probably the easiest thing to do would be to square out the integrand, 0 to 4, x squared plus 2x plus 1 dx, and then just integrate it from there. But I have no problem with you checking your answers, and we can check our answer this way. Math, 9, 0 to 4 of, I think I need parentheses in here, parentheses, x plus 1, right parentheses. And the reason I needed the parentheses is because I wanted to square this. Oops. All right. I've got this in a different mode, which is why I'm getting an N here. I've got it in sequence mode. Let's see if it works here nonetheless. There you go. And let's turn that into a fraction. So 124 over 3. Let's not forget something, though. There was a pi out in front. So, you know what? I think I can take a screenshot here. Copy. Oops. No.
I have a feeling we're all going to be internet app wizards by the time this thing's over with.
Yeah, I think so. So, there. Paste. There we go. So the final answer would be 124 over 3 pi. Because remember, you get that pi out in front. I don't like to put pi in here when I'm doing these things, because then when I do this answer to fraction trick, it won't give me anything. It'll just keep on giving me the decimal answer, and that's not helpful. So that's why I left pi out of this. So nice, nice. All right, rocking and rolling. Other questions from the audience?
I had a question. I think it's, which one is this? 6.1? 6.1, number 2.
Can you read me the problem?
Yeah, I've got the upper curve is 5x or 5e to the x, and the lower curve is 5x e to the x squared. And the bounds are from 0 to 1. I'm guessing it's an arithmetic error, but I keep getting 5 halves e minus 5, and of course that was incorrect.
Okay. Well, tell you what, let's look at these graphs here and just make sure that we're in good shape as far as the graphs are concerned. As far as the upper and lower one, did you say the limits were 0 to 1?
Yeah. Yeah, it's the graph shows it pretty clear. The red curve is the upper curve, the blue curve, the lower curve. So it's 5e to the x minus 5x e to the x squared. And so I got as far as you roll out the 5 on both of them. So you have 5 integral e to the x dx minus 5 integral x e to the x squared dx. And I think that's as far as you can go with simplifying it like that. So I think you should be able to just dismiss the 5 until later on in the problem and just work out e to the x minus x e to the x squared from 0 to 1, and then multiply whatever's left after all of that by 5.
Okay. So let me see. I think you used red and a blue. I'll do likewise. And this should be good enough. Let me cut this little slice out of our picture. There. And we'll paste that back into OneNote.
Yeah, the main question, I think, because I'm fairly confident it's an arithmetic error, because this one should be fairly easy. When you have e to the anything, the integral is always going to be e to whatever the exponent is. Like you could have x squared, x plus 1 quantity squared, like whatever. It's going to be e to whatever that is.
Not exactly. It has to be just e to the x. It can't be e to the x squared. In this case, to integrate this, you're actually going to have to use a u-substitution for that second part.
Okay. All right. That's probably where I went wrong then.
All right. So Let's take a look here. So these are our two functions. Y equals 5e to the x, and this one is y equals 5e, excuse me, whoops, 5x e to the x squared. So I'm just going to keep on doing this because it's such an important part for section 6.2 that I want to continue it.
Yeah, because something tells me we'll see something that looks just like this, except we have to spin it around one of the axes.
Yeah, yeah. I mean, there are shapes where you're going to have to do this in another direction. That is, whoops.
Now, and Calc 2 loves throwing these kinds of questions at us too, so this is good stuff.
Yeah. All right. I'm not sure why this is disappearing, but I want to find the area of that one rectangle. Area of one rectangle. And it's gone again. I just don't know why it keeps on evaporating. That area is going to be the height times the width. And let me just try this one last time. So let's start out with the easy part. The width is what?
dx?
Dx. And the height, it's gone again. I don't know. Is it disappearing from your screen? Because it keeps on disappearing.
Is it a color
Yeah, it
issue?
disappears.
Disappears?
Yeah, it keeps on disappearing. I don't know what's wrong with
Maybe
it.
try yellow.
Is that showing up okay?
Yeah, I can see it up until you start doing something else.
Yeah, up until I actually want to look back at it. All right, so the width is just going to be our dx. The height is going to be top minus bottom, so it's going to be 5e to the x minus 5x e to the x squared times dx.
Right, that's what I got.
And it's gone again. It's just so annoying. All right, so we're going to integrate that from, I'm done trying to draw on this thing.
See, and at this point, I split it up and I had 5 integral e to the x from 0 to 1 minus 5 integral x e to the x squared from 0 to 1. Of course, dx on both.
Yes, I mean, that sounds good. All right, so I'll split that up in the next step here. 5x e to the x squared, all dx. And you're right, we'll use the linearity properties of the integral to split that up. I'll take the 5 out in front, 5 times the integral from 0 to 1 of e to the x dx minus 5 times the integral from 0 to 1 of x e to the x squared dx. All right, this one, the antiderivative of e to the x is just e to the x. So I'll get e to the 1 minus e to the 0, which is going to be e minus 1.
E minus 1, yep.
All right, so we'll just leave that one alone. Let's focus on this one because that one's going to need more work. In order to integrate this one, you can't do it directly. You need to make a u-substitution. So
Okay, that's where I went wrong then, because I had it where it was x squared over 2 times e to the x squared.
okay, so what we'll do is we'll let u equal x squared. Du would be 2x dx. And let's also change our limits of integration.
Okay.
U of 0 would be still 0. 0 squared is 0. And u of 1, oh, guess what? Our limits don't really change. But that's the exception, not the rule. So this becomes, let's see, wait.
Should be
We've almost
5
ready.
halves
Yeah. So
e to the u.
I've got an x dx here, x dx here. I got to get rid of the 2, so it's going to be 1/2 du equals x dx. So now I can do my u substitution. X dx There we go. So it's going to be 5 times the integral of e to the u
It's going to be 5/2.
times 1/2
Oh, never mind.
du,
Sorry.
0 to 1. And you're right, I can take that half out in front, 5/2. 0 to 1 of e to the u du. And that 5/2 is just a constant. And I'll end up with the integral of e to the u, but that's just e to the u.
Exactly.
And I'll end up with e to the 1 minus e to the 0 here.
Yeah, and then e to the
Now,
0.
let's put those together. Are you okay with our result from here?
Yeah, from here, this is easy because then it's just drop all the brackets and then combine all the like terms.
Let me give you a cool way to combine the like terms. E to the 0. If you notice, this and this are the same.
Mm-hmm.
So all I have to do really is subtract the coefficients right there. So if I do 5 minus 5/2, well, that's 10/2 minus 5/2. It gives me 5/2 again. So it just gives me 5/2 times e to the 1, which is just e, minus e to the 0, which is 1.
Right. Okay, let's see.
Beautiful.
See, oh crap. I have 5/2 e minus 5, and it should be 5/2 e minus 5/2.
Yeah.
Okay.
So if you distribute that, then yeah, you get the minus 5/2. Cool. Nice. Nice. And a good example of our u-substitution as well. So, all right. Doing good. Doing good. I do remember at one point seeing something like this, a sine of 2x over, is it sine squared of x dx or something like that. And this one becomes kind of a real pain, because in order to make any progress on this, you got to turn the integrand into something that you know. So the trick here is to remember that there's a cosine or a sine double angle identity. It looks like this: 2 sine of x cosine of x over sine of x dx. And I don't remember if this is exactly the right problem. Actually, it's sine squared. But I'll write sine squared as sine of x times sine of x. And I think you can kind of see what's coming. You cancel out one of those sine of x terms, and then you're left with, you know, something a little bit that might be a little bit more manageable. And it appears to me I didn't quite figure out exactly which problem it was. So it'd be a 2 times 1 over sine of x times cosine of x dx. And I probably might have should have had these upside down from each other or something like that. And this would have worked out better. But if you notice in the homework, I avoided something like that. So I figure that you guys have enough challenges with the virus and stuff like that, and being online, even though you didn't sign up to be online, that I avoided problems that require you to know, for instance, the double angle formula. But it's a good question. If I did see something like that on the horizon, I'd give you a heads up. I'd say, hey, don't forget. Now, there is one exception to that rule, and that one exception would be that sine squared of x plus cosine squared of x, I expect you to know this one.
That equals 1.
Yeah, that equals 1. All right. So
Cosine over sine, isn't that tangent? Or is that sine over cosine?
this would be the cotangent. So yeah, I guess we could do this as twice the integral of the cotangent. And actually, from there, I mean, you can do this one. Actually, let me not write it like that. Let me just leave it as cosine of x over sine of x. And what you can do is you can do a u-substitution here, right? I mean, this is perfect for a u-substitution. Now, The question is, what do you let u equal? Because you know that sine and cosine are derivatives of each other, at least within a constant. But what do you let u equal?
You would want it to equal the numerator, I would think, because you're, oh no, you wouldn't.
Yeah, so let me just show you, and this is a great teaching example. Let me show you what can go wrong with a u substitution. If I let u equal cosine of x dx, excuse me, not cosine of x, how about just cosine? Come on. There we go. Then du by dx would equal minus sine of x. And du would equal minus sine of x dx. And then you go, well, wait a minute. My sine is in the denominator. There's no way this is going to work. So like, so that's a problem. So what can you do about it? Well, let's get rid of all of this. Let me try it again. Last try. There we go. Let's start again with your second choice, which is u equals sine of x. And then du would be equal cosine of x dx. And the nice thing is that I've already got that in the numerator here, right? That's right there. So that's my du term. And then what am I left with? I'm left with 2 times the integral of du over u. But that's just the log.
Du, right, yeah, so it's
Yeah.
2 ln u.
2 ln of u plus your constant, and then 2 ln of sine of x. Beautiful. So that actually was a great question. Yeah, maybe I should put that one on the review. I don't know. No, it's okay. So
We'll see plenty of stuff like this next semester.
yeah, you will.